Greetings. Once I came across PID-tuning technique, and it was initially keep Ki equal to 0. Kp is a ratio of P output and process variable. Second step, apply Ki equal to Kp, and then third step, manually increase Ki to maximum value that it did not count on the shot. In my representation, that means the first step, apply Kp equal to reciprocal K plant. Second step, apply Ki equal to Kp, the same reciprocal K plant. And the third step, increase Ki while closed loop remains non-oscillating. And I thought, what if I a little bit play with math to and this method, this technique. So, planned transfer function is first order log. Find the closed loop transfer function. It looks like this. Then apply Kp equal to reciprocal K, planned K, and we get this. And here two things quite interesting. If we apply Kp reciprocal K planned, the closed loop steady state is half of set point. This first. The second, in this case, T of closed loop is a half of T of open loop of planned transfer function. Look, we can use step response to find the K, planned K, or we can do absolutely stupid things to just play with Kp. Let's play. We want to get a steady state in half of set point. It's 0.5. Okay. Too much. Let's make it little less. Nope. Better. Okay, we get it. Steady state of closed loop is 0.5 of set point. Next, let's add I term. Apply P controller. Find the closed loop transfer function and here the characteristical equation. Solve it for S and find this. And here is discriminant. One more interesting thing. If this part is negative, then roots have imaginary part. In this case, system oscillates. If this part is positive, then one of the roots, one of the closed loop pole, getting greater. It's not good for system stability. So it is the best when this part equal to 0. So find Ki. So this equation and find Ki equal to 1 divided to Kt, planned T and planned K. What means it's Kp divided T planned, and at its turn it's equal to Kp divided to twice T of closed loop. Let's check it. T closed loop is about, I would say, it's 0.3 of set point or 0.6 of steady state. And the system reaches this value, it's 5 seconds, at 5 seconds. So let's apply 5. and Ki is 0.025. And as you can see, closed loop t, the time then output value reaches 0.6 of that point is 10. It's equal to open loop time, lag time. So what's next? The second step, I apply KC, that's P gain, or common PID control gain. Closed loop transfer function, we get this or this. So what we get? We get for system where plant can be quite good described by first order lag. You can get P controller with common gain where you can regulate speed of closed loop by KC and mathematically find KP and KI. Let's see what will happen when we increase KC. Faster, it's faster and faster. And theoretically you can reach absolutely fast response, but unfortunately it's not achievable in real systems because it have higher orders. Let's try to work with higher order lag, second order lag. So apply PID controller, find the closed loop transfer function, take characteristic equation and collect by S, by orders of S. And I want to interconnect these members with this. I hope you understand what I do. Okay, let's remember what we get previously and apply this to this and find new expressions. Then we equate this part to this part here and this part to this part here. Find A and equate these expressions, this expression to this expression, and solve the equation for KD and find KD. Blah 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 blah. So KD is equal to 0.225 of second order KP divided by KI. So now let's apply it for tuning. How should it work on practice? Okay, how to use it. Closed loop transfer function. Planned model is 8th order lag to show this method works not only at first or second lag. DSP, it's the difference between set points, initial set points and set point and new set point. Let it be 5. Okay, let's start with extremely low KP value. So response steady state is 0.04. So let's put it in this formula and get new KP value. Apply new value and we get steady state, I don't know, 1.6 maybe. Let's recalculate. New value, new steady state, it's about 2.1, I don't know, 2.1, and apply new KP value. Okay, that's enough. Now let's compute KI value which system reached at 0.3 of set point or 0.6 of steady state. It's half of open loop T. So closed loop reaches 0.3, it's 158.1.6. It's somewhere here, and it's about 5, let's say it's 5.5 second. So we calculate KI, initial KI value, apply it, and I use this empirical formula. I want to put this point to set point middle. I want to put middle or between first max and min peaks. It's somewhere here. I want to put this point to 5 to set point. So I'm use this empirical formula and get new KI value, apply it, and what we get here. Okay, apply this value. Now the KD calculated by this formula, apply this KD value, and we get this. And now if we want to put middle point between max and min, I don't know, 4.8. now if we want to put this on set point, we can do this, but if it's not allowed overshoot or oscillation in your system, it's obviously we should to decrease KC value, and step by step we reduce, and we should actually increase KI. Again, use this formula. I want to put this point to here, and I'm find new KI value, apply it, and apply it here. But it's still overshot, and I'm again reduce KC 0.8, and I would say it would be okay, it's good enough, but you can reduce it a little more and a little bit increase KI, so something like this. I do know what real PID controllers, PLC instruction or so on, don't use this form of PID controller. So I show you how to recalculate it to most common forms of PID controller. Good luck.